In this part of the computational intelligence course related to fuzzy systems, we continue fuzzy relations. First, we will see how the inverse of a fuzzy relation can be represented, and then we will cover the definition of composition of two functions, and we will examine it in detail through examples. Consider, for example, the membership matrix R. Here we have elements for entry xy, with entry rxy having value, the value of the relation at point xy. Its inverse, shown as r to power -1 on yx of a relation on xy, is a relation on y Cartesian product x defined by the inverse at point yx is equal to the relation xy. For each x, element of reference set x, and for each y, element of reference set y. So, the inverse of the relation is the inverse of the matrix xy, representing the inverse yx is the transpose of the relation matrix array for the relation xy. So, if we consider the two-dimensional array by taking the transpose, we obtain the inverse of the relation. The inverse of a relation is equivalent to relation itself for any relation. Consider binary relations P on xy and Q on yz with common set y. The standard composition of P and Q is defined as xz is the element of the standard composition PQ, if and only if, for some y in the reference set y, such that xy is element of the relation P and yz element of the relation Q. In the fuzzy case, this is generalized by, this is the standard composition of the fuzzy relations at a point xz is assigned value such that for any point y in the reference set y, consider the pair P relation value at xy and the relation value at q, yz, and compare this to, take the minimum one, and then among all these y values, choose the superior of them. For every x in reference set x, and for every z in the reference set z. If y is finite, superior operator is replaced by the maximum. Then standard composition is also called max-min composition. The inverse of the max-min composition follows from its definition. P composition Q inverse is equivalent to Q inverse composition P inverse. Notice that here the order of P and Q is changing, and also for P the order of Y and X is changing. We are considering the inverse. And also for this one, the order of z and y is changing because we are using the inverse. Its associativity also comes directly from its definition. If we apply standard composition first between P and Q first, and then standard composition with R later, this is equivalent to first apply the standard composition between Q and R, and then standard composition with P and result of this. And here notice that the order of P, Q, R is the same in both sides. Note that the standard composition is not commutative. That is, standard composition PQ is not same as standard composition QP. Matrix notation for standard composition, in the matrix notation, for each entry ij, it is standard composition of entries with PRK, the P array, and QKJ in the Q array, with Rij is set to maximum of the values here, PIK, QKJ, we are choosing the minimum one, and among these minimums, we are setting the maximum value as the value of Rij. Meanwhile, we are considering each possible K value. Here there is an example. For example, here we have relation P and relation Q. We are trying to find the standard composition P, composition Q, and we are trying to find out an array for R. P and Q are fuzzy relations, and the resultant standard composition is also a fuzzy relation. In order to calculate the value of the R11, then we have to consider P1, the row P1 here, and here the value of row is 1, but we are changing K from 1 to 3. And here the second entry, second one is also 1, so we are considering the first column, first row, first column, R11. So for this one, we are considering the column 1, but we are changing the row. Here we are changing K from 1 to 3. So here, for R11, we are trying to find the maximum of these minimums. And these minimums are, here we are setting P, we have 1 here, and for Q, we have 1 here always, for all of them, but we are changing the value of K. So P11, Q11, P11, and Q11, we have to choose the minimum of these two, 0.3 and 0.9. And minimum of P1 to, now K is 2, Q to 1, these are 0.5 and 0.3. The minimum of these two should be chosen. And for K is 3, we are considering P13 and Q13. 3, 1, this one, and the minimum is 0.8 and 1. If we consider all this minimum is 0.3, this is 0.3, and this one is 0.8. We are taking the maximum is 0.8. Because of that, R11 is 0.8. Or let's try to find what is R32. R32, here we are setting I23, and we are changing K, and we are setting this J to 2. And again, we are considering the minimum of each pair while we are changing K, and among those, we are taking the maximum. So consider this one. We are considering P3, 3, 1, 3, 2, and 3, 3. Meanwhile, we are considering Q, 1, 2, 2, 2, and 3, 2. We are comparing one by one, 0.4 and 0.5. We are choosing the minimum, and 0.6, 0.2, and also 0.5 and 0. For each pair, we are considering the minimum. So here, minimum is 0.4, for this one 0.2, for this one 0. Among those minimums, we are choosing the maximum. So the result is 0.4. So here the value of the composition for R32 is equal to 0.4. Here there is another example for the standard composition. Consider the following phase relations for airplanes. Relation A between maximal speed and maximal height, and relation B between maximal height and the type. For the relation A, we have different levels of speeds for the maximal speed, and here also we have heights. And this is a relation between the speed and height. It has some values between 0 and 1. And this is the relation between maximum height and airplane type. Again, we have some values between 0 and 1. Now, we are going to find the composition of A and B speed type relation. Here there is a relation between speed and height, and here height and type. Then we are trying to find out what is the composition to obtain relation between speed and type. For example, to find the value speed 4 and type 2, we are considering this row for different heights, and for the same heights, we are considering type 2 here, and one by one, we are comparing and choosing the minimum, and then we are choosing the maximum among them. So the minimum 0, 0 is 0, 1.3 is 0.3, and 0.91 is 0.9. We are choosing the maximum of them, 0, 0.3 and 0.9. Maximum is 0.9. So in this manner, all the values are calculated. So this is like matrix multiplication. This is the row, this is the column, and one by one we are comparing. In order to compute the composition, we can use also flow scheme. For example, in order to find out what is the value of the composition at point S42, we are starting from S4 and going to each possible height value. And from these height values, we are going to the type T2. So we are starting with S4, looking for each possible height, and then we are going to T2. And this is the values here is used from the relation. We have 0 for this connection, 0.3 for this one, and 1 for this pair. And also we are considering the relation value between height 1 and T2. It is 0. Height 2 and T2, it is 1 here. And height 3 and T2, it is 0.9. For each path, we are considering the minimum. This is 0 and 0, minimum is 0. And this one is 0.3 and 1. Minimum is 0.3. And for that one, we have 1 and 0.9. The minimum is 0.9. So we are comparing each pair. So we are considering the fuzzy values on the path. There is no need to compare minimum 0, 0. It is already 0. We are going to find the maximum. So this will be smaller than the others. So consider this one, 0.31. So minimum is 0.3 for this line, for this path. And for the next one, it is minimum of 1 and 0.9. So this is 0.3 and 0.9. If we take the maximum of them, we obtain 0.9 as the value at S42, the value of the relation composition.